In this video, we're going to look at the same operations that we already know how to do with geometric vectors and focus on how to do those same operations algebraically now that we have a way of expressing vectors in an algebraic form. So those would be the operations of addition, subtraction, and scalar multiplication. So I've written here two vectors. One is vector A. It has an x component of a1 and a y component of a2. The other vector I've written here is B, with an x component of b1 and a y component of b2. And I've written them in both column vector form and based on basis vectors. So you can see both algebraic forms of writing vectors are written below. And what we're going to do is look at each operation individually and establish a rule that will allow us to determine the results of addition, subtraction, and scalar multiplication using these algebraic representations. Let's consider the operation of addition first. So we're going to add together a vector A and a vector B. And for the purposes of visualization, I'm just going to draw kind of a generic vector A and another vector B. Now we know when we're adding them, we have to draw them tip to tail. So I'm going to have vector B starting immediately after vector A. And so what this does then is it allows me to draw my resultant vector A plus B as starting at the beginning of A, going along and connecting straight to the end of B. So that vector would be the resultant A plus B. Now we know how to do that geometrically. That's already established. What I want to focus on is how do we determine that algebraically? And the key to figuring that out is actually based on looking at the components of the individual vectors. So remember, vector A is based on a horizontal component of A1 and a vertical component of A2. And similarly, vector B is based on a horizontal component of B1 and a vertical component of B2. So you can see how each of those vectors are built based on a horizontal piece and a vertical piece. And so figuring out how to do addition algebraically is just as simple now as looking at that resultant vector and saying, well, what's its overall horizontal component and its overall vertical component? And you can see, and I'll draw this in red, that overall, to go from the beginning of A plus B to the end of A plus B, the horizontal distance that we have to go is a combination of the horizontal distance that we did for A plus the horizontal distance that we did for B. And then vertically, it's the same idea. The vertical distance that I have to go is a combination of the vertical distance we went for A plus the vertical distance we went for B. And so those become the components then of that resultant vector. If I wanted to find, in general, the vector A plus B, its components as a vector will be the sum of the x components of the two vectors involved in that sum. So if I'm adding vector A and vector B, I would take the x component of A and add the x component of B. And for the y component, I would add, again, the y components together to get my y component of the overall vector. So when you're doing vector addition, and you're doing it algebraically, adding the two vectors is quite literally the same as adding together their two components. Now, that same logic we used for addition can actually be extended to all the other operations we do with vectors. So when I do a subtraction with vectors, it's the same idea. The components of that resultant vector are based on subtracting the components of the vectors that are involved. So I would subtract the x components from each other, and then I would subtract the y components, and that gives me the components of my resultant vector. And even for scalar multiplication, if I want to expand the overall size or condense the overall size of a vector, so let's say I was doubling the vector, that can actually be done by doubling the x component and doubling the y component, or having the x component, so dividing it by 2, and then dividing the y component by 2 would divide the overall length of the vector by 2. So scalar multiplication is also just as easy as multiplying each of the components by that same scalar. And you can even see how overall that multiplying of components would change the overall magnitude, because now if I go to find the magnitude of that new scaled vector based on my magnitude equation, we know that we would have to take the square root of the x component squared plus the y component squared. And so if I work this out, I have k squared a1 squared plus k squared a2 squared. Here I can factor out a k squared, And once I've factored out that k squared, I can actually square root it. So I have k times the square root of a1 squared plus a2 squared. So that part on the right is just the magnitude of the original vector a. And so you can see here then, based on what I've worked through, that by multiplying the components by whatever scalar multiple I wanted to use, I am actually changing the magnitude of the vector by that amount. I'm scaling it up or down based on that quantity. And so then, as far as algebraic operations are concerned with vectors, I really just have to add the components if I'm adding, subtract them if I'm subtracting, multiply them if I'm multiplying. So let's look at some vectors and just work through an example. So let's say I have a vector a and b as I have given on the left. So vector a is 2, 3, vector b is 3, -1. If I wanted to find the resultant for a plus b, I'm just going to take my x components, 2 and 3, and add them together, and my y components, 3 and -1, and I'll add them together. And so the resultant vector a plus b has components 5 and 2. And so now I have an algebraic way of expressing that resultant vector. I would have come to those same conclusions had I drawn those vectors tip to tail on a grid and added them up that way. I would have been able to realize from the grid that a plus b had components 5 and 2. But you can see how it's really easy to work through algebraically just by adding them. I also wanted to show you how it works with basis vectors with the example on the right. So I have vectors c and d written out. And let's say I wanted to find c minus d. So what I can do then is just take 2i plus j and quite literally subtract the vector d, which was minus 3i plus 2j. And this is the really interesting thing about basis vectors, is they almost work the same way as variables. So here, I leave the 2i plus j unchanged, but I'll distribute that negative in and have a plus 3i and a minus 2j. And then I basically can gather like terms. So 2i plus 3i gives me 5i. J minus 2j gives me a minus j in the resultant vector. And so now I have the components of that resultant vector c minus d. I know it has an x component of positive 5, so it's going to the right 5 units. And it has a y component of -1, so it's going down 1 unit. And I was able to figure that out very easily through some simple algebraic operations. And the same works too for scalar multiplication. I could scale up the vector b so that it's 3 times its size, and so that's just going to involve multiplying the components by 3, so I'll have 9 and -3 as my components for that new vector. So all these algebraic operations are fairly straightforward once you have the vector expressed in column vector form or basis vector form. Even changing the direction of a vector. So let's say I wanted to have a vector going the opposite direction of c. So a vector like -c. That would literally just involve multiplying the components of that vector by a negative. So it was originally 2i as the x component there. It's now -2i. And it was originally a positive j, so now it's a negative j. And now I have a vector that's the same length as c, but going in the opposite direction. So algebraic operations with vectors are going to be incredibly useful going forward, because we do spend far more time dealing with algebraic vectors than we do geometric vectors. Both representations are very useful, but as far as simplicity, if we're working through a lot of operations really quickly, or we're trying to model something in real life, it becomes a lot easier to represent things algebraically. And so those operations are going to help us going forward tackle a lot of challenging problems. But even now we can see how algebraic operations with vectors might help us find a unit vector in the direction of a given vector. So I've given here a vector p, which has the horizontal component that is going to the right 3 units, and then the vertical component going up 4 units. And I want to find a unit vector that's going in the same direction as that vector. And so you can tell from this, it's not a unit vector as it stands right now. If I find the magnitude of p, it's the square root of 3 squared plus 4 squared. So you get that the length of that vector is 5. So certainly not a unit vector, which would have to have a length of 1. This has a length of 5. It's 5 times longer currently than it needs to be. If I wanted to find a unit vector in the direction of p, though, it just becomes a matter of actually scaling down the size. It currently has a length of 5. I want it to have a length of 1. So I need something that is 1/5 the size. And so determining that is actually fairly straightforward. So a unit vector in the direction of p, first of all, notationally, I won't use the arrow. I'm going to use a hat. because I've been using that to represent all of my unit vectors. That's actually a common notation. So a unit vector in the direction of p I would write as p hat, not p with the vector arrow. But then all I really have to do is say that a unit vector in the direction of p is actually 1/5 of p, because the magnitude of it was 5. If I scale that down to 1/5 of its normal size, I will have a unit vector. And so that just means I need to find 1/5 of the vector 3i plus 4j, which based on scalar multiplication is actually really easy to do, because I just have to multiply in that scalar multiple of 1/5 into those numbers in front of my unit vectors, or my basis vectors. And so I do 1/5 times 3, and I end up with 3/5 of a positive x vector, and 4/5 of that positive y basis vector. And so now that's a unit vector that's still going in the same direction as p, but again, p was length 5. This is now 1/5 the length, so now this is a unit vector going in that direction. And I can do that really easily now with scalar multiplication, whereas beforehand, geometrically, it would have been considerably more difficult to actually scale it accurately. It's one thing if the vector is only made up of a horizontal component or a vertical component. That would be fairly easy to scale down to a unit vector, but as soon as we have vectors that are made up of a horizontal and vertical component, it becomes a little trickier geometrically. But algebraically now, we have a very straightforward way to do it. In general, if I have a vector u, it has a unit vector, and the unit vector can be written as the original vector multiplied by 1 over the magnitude of the original vector. So that's just the general rule for finding a unit vector of any vector you would want. And so those are the key algebraic operations with vectors. Certainly there's more to come here. We're going to keep building on these, but these operations are really going to define how we work with vectors in all contexts going forward.